Oh, no, no. Let's see. Good morning, everybody. Good morning. Oh my God, I stayed up so late last night. It's terrible. I was up at like um, like 2:30 or something. Couldn't sleep. Stupid alarm went off at 6:30. I turned it off. Didn't wake up until 7:37. I looked like hell. I managed to grab a shower and cup of Joe. Oh, you can't see my coffee. A cup of invisible coffee. But anywho, um, our homework's due Friday. Our leisurely stroll through chapter 5 here. Not so leisurely, but in any case, kind of leisurely. And tell me if I'm repeating myself. Did I talk about standard editions that go through the blood and gore last time? I don't think so. Let's
I
see.
think maybe we started it, but I don't know about I don't know if we
Yeah.
got all the way through.
Thank you. Thank you, Ryan.
Yeah.
Thank you. Okie dokie. Everybody's hoarse this morning is like, morning. I am so hammered. Anyway, there's this, and this word came up for me. It's called desvelado, trasnochado. They used to say it in Colombia, and it's when you stay up all night, and you've been partying all night, and the next morning you're all. I didn't party or anything. I didn't drink or anything. I just I I studied, and I got an aluminum bar that I'm working on a little project for setting up a digital readout on my mill. So I've got to mill that down, and I was excited about that. I mean, stupid thing, but anyhow. So the standard edition here. That's what we're talking about, right? And um, there's another. The standard edition. Basically, the idea is that whenever your method, or it's easier to think of as an instrument, like whenever the instrument you're using to measure something, when that thing has a dependence the on the sample, So for example, I think I did talk a little bit about like there's like you could imagine measuring iron in blood or something. And if you do that by zeroing your instrument with water and then measuring, say, iron nitrate, in water, those aquated, they're called aquated ions, right? They're not going to be they're not going to be seen by the instrument in the same exact way as the iron in the heme, right? So it may be that your instrument is more sensitive to the iron in heme, or it could be less than the iron in the water. So if you calibrate with water ion and you measure heme iron, then the iron in heme the number you get isn't going to come out right. You won't know. So that's one example, right? And so the best way to approach this is to calibrate using standard reference material. And they're just not always available. Basically, you'd have to buy blood with known iron content, or alternatively, you could treat your sample, your blood or whatever. You could oxidize it with nitric acid or something. Try and make the irons aquated, and then measure them against iron nitrate, that type of thing. But one sort of generalized weapon that we have in this battle is called standard additions. And there's something about standard addition that I would like to emphasize at this point here. And that's that, oh geez, that's ugly. Thanks. And that is that oh geez. There are basically two approaches. To standard addition. One is when you have a non-destructive method. So that is when what you're doing doesn't use up any of the sample. So, for example, you could be taking a UV vis absorption and you're just putting it into a cuvette and putting a little in the instrument, and it doesn't change it in any way much. So that's called non-destructive methods. And they tend to be a little bit complicated, a little bit weird, And they're slightly less popular, or I don't know what to say that. I could be wrong there. And there's for destructive methods, right? And these are this is when the instrument uses up the sample and turns it into vapor, does something to it that you can't use it anymore, right? And these methods are these require that you have enough sample that you can split it into a bunch of subsamples, let's say. Right. So in number one, you let me switch over to my document camera. Oops. Turn it on. Document. Oh shit. It's the second iteration. There we go. It's still alive. It's alive. Let's see. Okay. So for the non-destructive, you have like a sample of stuff, right? Right. And you're maybe making a measurement, measure the light transmission. At some wavelength, right? Sorry, this sucks. Oops. And then then you add standard to this, and then you add more, and then you get volume changes, and you get concentration changes, and you kind of have to distinguish between X, which is called the analyte, and S, which is the standard. But they're actually the same thing, right? The same chemical, right? This is maybe Fe in the sample. This is maybe Fe that you added from that that you added. And so that they just, I don't know, it tends to be a little bit complicated. We're going to touch on a couple of those. We'll go over a couple of the problems, but then we'll talk about the destructive method. And the destructive methods, basically you take your sample, and the same volume of your sample, and then you put a spike, and then two spikes, and then you top them off with water, for example. And so you try, what the effort here that you're trying in both of these is to make the matrix similar for the sample and the standard. So let's dive in here. Okay, so I'll add these notes in here, I promise. Okay, so standard addition, I think I went over this, I'm not sure. But this is for the non-destructive approach. So you just spike your sample, right? So you've got an initial concentration and a final concentration. You've got an initial signal and a final signal. And all you have to do is deal with how the final concentration is related to the initial concentration by the volumes involved, right? Because you can control all the volumes, right? You've got VI over VI plus VS and VS over VI plus VS. This is the total volume after the spike. And that's the initial volume. And that's the spike volume. Right? So SF is the spike volume after you spike your sample. So it's like once you pour the standard in, it gets diluted by this factor. So SF shows up here, right? And XF shows up because it has to show up, right? And then XI has to show up, and then these are the two signals that you measure. So it's, on some level, it's fairly straightforward. But does anybody have any questions about this sort of formulation of things? Everybody good? Elizabeth?
Yep.
Yes. Elvin, good? Okay. That was I think that meant good in the language of static. Okay. So we can go through this one here. What do you have up? Serum containing sodium gave a signal of 4 millivolts, and then you spike it with Vs and Cs, this original volume, right? Then it gave this signal, right? So the trick is to find the concentration of sodium in the serum. So here is Ci, right? This is the amount of sodium in the sample. And that's the amount of sodium in the sample, right? It's just an unknown, right? So all we're going to say is that this concentration, this is Xi, right? And its signal are proportional. And the concentration and the signal of the final spike solution have the same proportionality, basically. So that's how we can justify ratioing them like this, right? This equals this, and this equals this, therefore this over this equals this over this. You know, it actually always works, I think, mathematically. I hope so. Otherwise, I'm just going to have to hang it up. Try to find a non-destructive job. Anyhow, 0.95 times sodium. This 0.95 is from this value here, 95 mils, I think. Yeah, it's from this 95 over 100, right? So it's X of I times VI over VI plus VS, right? And S sub F here is 0.104 molar, right? That's 2.08 molar times 5 over 100. So SI, here's XI times 0.95. This is XF, and this is SF. The original sodium that we added. And this is the amount of spiked sodium. These are all molarities. Right? This is the signal, right? And then you just do a little bit of algebra, and you can solve for sodium there. Right? And I'll see if I have a work through on this next one. I'm pretty sure I do, actually. Jeez, it's so stupidly long. Yeah. Actually, I redid this one with all the blood and gore. And then, yeah. Okay, so I guess I'll go ahead and do this one just for giggles here. So if we have a sodium sample, you know, it's like a beaker with some sodium chloride in it, right? And we directly introduce this into an emission spectrometer and we get 4.41 millivolts, right? And we take the same 95, then we take the same 95 mLs, right? So this is going to be 95 mLs, this will be 5 mLs, right? And this is going to be our spike. Oops. And this is going to be 2.08 molar. These are high concentrations, right? And this is our unknown. This is our Na plus is unknown, right? And then so we do our spike. And this gives us 7.82. So this is a good standard addition, right? We roughly doubled our signal, right? And so so what we want to do is we want to set up our variables here. So VI is 95 mLs. VS is 5 mLs. VI over VI plus VS is equal to 0.95. Or I'm sorry, this is 95 over 100, right? 0.95. VS over VI plus VS is going to equal 5 over 100. It's going to be 0.05, right? And then so to set up our standard addition here, we've got Xi over Xi times 0.95 plus 2.08. That is the stock concentration times 0.05, right? Is equal to 4.41 over 7.82. Once in, we just sort of like multiply this out. And I'll drop the brackets for that. I'm just going to say X over 0.95X plus 0.104 is equal to 0.561. I'm trying to find X. So I'm going to turn this. So I don't know why exactly I flipped this over, but I'm just going to go with it because I did. But so this is equal to this is equal to 0.95 plus 0.104, 0.95x over x is equal to 1.773. And then we can break this up. 0.95x over x plus 0.104 over x, 0.773. These x's cancel.
Or you could have just multiplied 1.773 by x, and you would get rid of x on the other side.
Multiply 1.773 by x?
Yes, and then the other side x will go out.
That's right. That's right. That would be more efficient. Thank you, Alvin. That would be so more efficient.
Yep.
Okay. That's right. Okay. Well, there's a couple of ways to do this, and Alvin has a better way. Let me finish this, and then maybe we can show you Alvin's way. It's
Sure.
Yeah. I just don't want to totally publicly screw up everything. So, so in any way, so 0.104 over x is equal to 1.713 minus 0.95 is equal to 0.823. And then x is going to be equal to 0.104 over 0.823 will equal 0.126.
Yep.
Okay, hopefully we came up with the same value. And Elvin's point was that we just multiply by x on both sides here. And that works. I'm sure it gets you there in fewer steps. So anyhow, this is how to do this. And this is not super common. This is only if you have a non-destructive method and you're just adding, right? And then there's a whole big to do about how to, and this is same approach there. Then there's this whole thing, like if you take a sample and you just keep adding standard to that same sample, then you can get this complicated mess. And I just don't want to deal with it. We've got enough on our plates. It's just like more of the same. It's just kind of more algebraic hell to go through, from my opinion. So we're going to skip this one. This is also for a non-destructive method where you can just keep adding standard and measuring, and the volumes keep changing, and concentrations keep changing and everything. And I don't know. It gets to me, it gets a little bit complicated, but and you got to plot these weird things, on the various axes. So I've never done it, and I don't think we should teach it. So anyhow, that's my story, and I'm sticking with it. Okay, so this is a more common approach to standard additions, and this is where you split your sample into 5 parts, right? I mentioned this before, right? 1, 2, 3, 4, 5. And then, let's say you could say 5 mils of your unknown in each flask, then add 0, 5, 10, 15, and 20 mLs of standard, and then dilute to the mark, to the 50 mil mark, right? So you got 5 of unknown and 50, right? Then the X, so what you do is you plot the signal versus the concentration of the spike that you added, right? This is S sub F here, right? So now the x-intercept of this will be minus x of F. So the original amount of stuff in there will be from the x-axis. It'll be negative, right? So here's an example, right? You do this experiment, you get an x-intercept of minus 0.235 millimolar, right? What is the original concentration in the analyte, right? Well, I can tell you right now, this depends on how we set it up, right? We took 5 mils of unknown. Oops, with red here. 5 mils of unknown and diluted to 50, right? And then what we get is that corresponds to 0.235 millimolar. So if you undilute it, you basically multiply by 50 over 5, you're going to get 2.35 millimolar here, right? 2.35 millimolar. Yes, sir. I'm such a dork. Stop me. Okay. Does that make sense? Somebody say yes. Elizabeth.
Yes.
Excellent. Good. I love it. Okay, so now here's an example with some hormone or something, and I don't know. I didn't do this one, I don't think. Yeah, I just did the 2.35 one. So oh, maybe I did do it. Hold on. Let's see here. 1 milliliter of blood. Yeah, okay, I did this one. 1 milliliter of blood was brought up to 25 mils, right? Okay. So this is a constant volume one, right? And all you need to know this is the need to know this value here, minus 4.2 parts per billion, right? And so basically, you just take this value and undilute it, right? So you multiply it by 25 over 1. So oops. There we go. So if we read the foils, then we've got 25 mLs here. And we take just 1 mil of blood here, right? This is a good one for this is a good one for Halloween, right? Okay. All right. So 25 mils, and then we QS with water or whatever, you know. And then we do this again a bunch of times, right? So it's 25, 1 ml of blood, each of them, right? And then this one will have some standard. This will have 2x of standard, you know. And then all of them are taken to 25 mils, right? We do the plot, blip, 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 and we get the XF is equal to 4.2 parts per billion, right? Or minus 4.2, whatever, can have negative concentrations anyways, right? So basically what you do is you say, well, if this is 4.2 parts per billion is equal to XF, then XI is equal to CI times XI is equal to CF times XF, right? So XI will equal XF times, so no, it's not V. Sorry, I screwed up. So XI times VI will equal XF times VF, right? This is a dilution formula. So XF here will equal XI times VI over VF. Shit. No, we're solving for XI. Sorry. XI will equal XF times VF over VI. Ah, Jesus. I have notes here. I still can't get it right. So this is equal to 4.2 parts per billion times VF, which is 25 mLs, over VI, which is 5 mLs. Right? So anyhow, this comes out to 105 parts per billion, right? Parts per billion, right? So now they want this answer in molar. So what we need to do is we need to convert the 105 parts per billion to molar. And so that's going to be 105 times 10 to the minus 9 grams per gram of solution. So, and then we're going to say that there's 1,000 grams of solution per liter. And there is 1 mole of analyte in every 373 grams. And this comes out to be 0.282 times 10 to the minus 6 molar, right? Wait,
Dr. Terry?
Yes, Alvin. Did I get this
4.2 times 25 over 5, correct?
What?
Yeah. If you go up, it's 4.2. That is not 105. That is 21 something. If you do whole thing, yeah.
Oh, really? Oh, I have a mistake. Okay. So,
because 4.2 times 25 is 105.
Oh, I forgot to divide by 5. Sorry. Okay.
Divide by 5, yes.
So this is 21. Okay. Call it 21 parts per billion. Thank you. Thank you very much, Alvin. Okay, and then so thank you. Extra bonus credits there. In the only in the spiritual realm, however.
Yes.
You get karmic return. Yes. Instant karma, right? Okay, cool. All right. So 21 parts per billion, right? Okay, so this is 10 to the minus 6. So this is, I'm sorry, this is now going to be something other than this, which is 21 over 373, whatever the hell that is. So this is going to be, this will be our X sub I in molar. It'll be some value there. I don't want to work it out. What do you get, Alvin?
21 over 373 is 0.056.
Okay, 0.056, then times 1,000, and divided by a billion. So this is times 10 minus 6.
Yes. And is that 9 or what is that solution thing?
This is a 9, right? And so we have to. This is parts per billion, right? The billion is 9, right? 10 to the 9. So this is 10 to the minus 9 grams per gram, right? And so 10 to the minus 9 grams.
Okay, so yeah, only 21 over 373.
Yeah, 21 over 370, but times 10 to the minus 6.
Yes. So 0.056 times 10 to the power negative 6.
Times 10 to the minus 6. So this is going to be 56 parts per billion. No, it's 56. Sorry, nanomolar. Because so this is equal to 56 times 10 to the minus 9. So that's 56 nanomolar. Oh my God, that was a bloodbath.
Cool.
It's too early. Too early to screw up. I knew I was going to screw up today. That's why I couldn't sleep. I think it would motivate me to work harder so I don't screw up. Somehow, I don't work that way. Okay. So I'll clean this up and post it. I promise. Okay. So the next subject here is called internal standards, and internal standards are basically these are instrumental only, pretty much. I can't think of a non-instrumental way to do an internal standard, right? And the idea behind an internal standard is that it's in your sample, but it's like it's not your analyte. So if you're measuring, it's easy to do elements. Let's say you're measuring iron, but your instrument is kind of fluctuating a little bit, and you measure iron and over, and it like drifts up for a while, then it drifts down, and then blah, blah, blah. It's like something weird is going on, right? You know, it's the best instrument for the job, right? But it has this fluctuation issue. What you can do is you can add, if you have many channels that you can measure in this instrument, right? You can add something else to it, right? You could add, say, yttrium, you know, or something weird that's not going to be in the sample from any weird, like, random source, but so that you know how much yttrium is in every sample, right? So you can add a standard, everything that goes in, and then you're going to measure. So if that standard signal goes down and up, or down, right? Then you know that the instrument sensitivity is going down, right? And so if you're lucky, and a lot of times you are, then that can be traced to something that's also affecting the analyte in the same way. So in that case, what you do is you measure the ratio of the analyte signal to the internal standard signal. And you keep the internal standard constant. It's really handy. Like, whenever you have an internal standard, and you have any doubts about your method, then go ahead and use the internal standard, because they're, you know, it can be very handy. You know, if it's not messing anything else up. So, so it's a known amount of a different compound, right? It's a different, you know, it's like it's like yttrium added to an iron sample, right? Something like that. hopefully there's no yttrium in your iron, right? But hopefully not. Okay, so it's useful when the response varies from run to run, or when sample loss can occur during sample preparation. I guess in this case, you'd have to add the internal standard at the beginning, and hope that its loss matches the sample loss. Kind of weird. And if it's chemically similar to your analyte, that's good. So that the matrix effects can be minimized between, the difference in the matrix effects are minimized so that the matrix effect for your sample and your analyte are the same. These are all weird shit. Don't worry about this too much. But if you think about it, it all actually makes sense, but it's a lot to go through, right? So here's a 1-point calibration example where you can take an analyte signal, right, and an internal standard. Oh, geez, they both have 10, let's say millimolar here. Geez, molar, God. I'm going to measure something at 10 molar. You can measure X, and then in this case, the sample, or the analyte rather, and the internal standard are separated on a time axis, right? They're resolved on this time axis here. So you got X and S, and the signal from the analyte divided by its concentration, right? What you want to get ultimately is a concentration of the analyte, right? Is equal to some factor F times the signal from the standard times the concentration of the standard, right? So if your analyte is also a standard and your internal standard is also a standard, then you can determine what F is, right? Right? You just, plug in all these other values and you get F, right? So if you got 0.08 molar X and 0.06 molar S, they gave these two areas, then you can figure out what your F value is supposed to be here. And I think that's, it's fairly straightforward to do this. F is 0.97 in this case. You just plug in everything else, right? And then, then what you do is you do the same experiment with the same internal standard, right? And you get the signal. You get the signal for your unknown. They call it A here for area, but it's the signal, right? And you solve this guy out for why would you solve it for SF? That's weird. Oh, well, I don't know what the hell they're doing here. Oh, yeah, they're just getting, I don't know what they're doing. Got all these numbers, you get F, right? Concentration of S. Oh, this is just multiplying this out, I guess. SF, right? And then you can multiply this, and put in all the numbers, you get that. So X was diluted from 10 to 25 in this preparation. So the original concentration of X in the unknown was this, right? So I have this all written out, but I just don't have time to go over it because we're out of time. Okay, so I'll stumble through this next time, I promise. And then we'll be done with chapter 5 by Thursday. Hopefully I'll be more coherent when we come back. And thank you all for listening. Thank you for coming. Thank you for sharing. And I will see you all next time, guys. Bye.
Thank you, Dr. Cheryl. Have a good one.
Thank you,
Thank
Professor.
you. Thank you.
See ya.